guys, come back to another video. Today, we will be talking about the moon's diameter. So, I want you to imagine that it is 2000 years ago right now. People think the whole universe is just Earth in the middle, the moon, the sun, the 5 planets, and the stars. The astronomers of that time wanted to know, how big are all of these things and how far away are they? But that wasn't easy. So, they started with the moon because it was the closest object. It also changed shape every month and caused eclipses. As for the Earth, even though we live on it, we're stuck to it. So it's actually pretty difficult to study it. But how could anyone measure the size of the moon? In 270 BC, a Greek astronomer named Aristarchus tried to answer this nearly impossible question. He didn't have a telescope. He didn't have a calculator. He didn't even know how far away the moon was. And guess what? He figured it out! He only needed 2 observations and 1 smart idea. His observations are that the moon and the sun look at the same size in the sky. During the lunar eclipse, the Earth's shadow is about 2 moons' widths wide where the moon is. His big idea: the sun is very, 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 very far away, and so is very, 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 very big. Now, imagine, how did Aristarchus come up with these ideas? And an even better question, how could he use them to work out the moon's diameter? Have you ever watched a lunar eclipse? It's amazing, isn't it? You can see the moon slowly being eaten by a shadow until it almost disappears. And then it turns into a spooky blood red color. Wow, what a spectacular sight. But do you know where that shadow comes from? Well, it's Earth's shadow. During the lunar eclipse, the sun, the Earth, and the moon line up almost perfectly, and the moon passes through Earth's shadow. People in ancient times had already figured this out. In fact, it was one of the clues that convinced them the Earth must be round. They also understood something that many people get wrong today. Earth's shadow isn't a cylinder, it's actually a cone, because they realized that the sun is incredibly big. So, the circular shadow that slowly covers the moon during a lunar eclipse isn't the same size as the Earth. It's actually a little bit smaller. The challenge is to calculate the ratio between the size of the moon and the size of the shadow. Back in Aristarchus' time, there were no telescopes, no computers, and no cameras. So, he had to make this calculation using drawings made by eye alone, which, of course, wasn't nearly as accurate. Naturally, that lack of precision affected his final result. In the end, he concluded that the Earth's shadow was about twice the diameter of the moon. Not bad at all! That was his first clue. Today, it's actually super easy to do, even with just a smartphone. Let me show you. In September 2025, I recorded a total lunar eclipse. I put the link to the video in the comments. I took a screenshot from the video and zoomed in on the moon. Then, I imported the picture into GeoGebra, a free online math tool, not sponsored by the way. Since only one circle can pass through 3 points, I created one circle by picking 3 points along the edge of the moon, and another circle by picking 3 points along the edge of Earth's shadow. Then, all I had to do was use GeoGebra to calculate the ratio between the radius of the 2 circles. The answer? 2.73. While the real value is about 2.65, that's incredibly close for a simple photo taken with a smartphone. But here's the really clever part. If Earth's shadow had been exactly the same size as the Earth itself, Aristarchus would have already known the moon's size. But since the Earth's shadow is actually smaller than the Earth and they did not know how much back then, he still had one more mystery to solve and will need more clues. Did you know that the sun and the moon have something amazing in common? They have almost exactly the same apparent size. It's a fantastic geometric fact. But what is an object's apparent size? An object's apparent size is simply how big it looks from where you're standing. In other words, it's the part of your view or the sky that the object takes up. If two objects are the same distance away, the bigger one will look bigger. And if two objects are the same size, the one that's further away will look smaller. Now, let's look at the sun and the moon. During a total solar eclipse, the moon passes directly in front of the sun and can cover it almost perfectly. Of course, some eclipses are a little bit different. During an annular eclipse, for example, the moon is just a bit too small, so a bright ring of the sun is still visible. I imagine that must have given the ancient astronomers a few sleepless nights from how confusing that is. But overall, these eclipses show something almost magical. The moon and the sun appear almost exactly the same size in our sky. This was the second clue Aristarchus used to figure out the size of the moon. Now, let's go back to the present. Today, we know that neither the Earth's orbit around the sun nor the moon's orbit around the Earth are perfect circles. Instead, their orbits are ellipses. Because of that, the Earth-Moon distance changes by about 5.5% and the Earth-Sun distance changes by about 1.7%. That means the moon's apparent size can range from about 90% of the sun's apparent size to about 106%. So sometimes the moon looks a little bit smaller than the sun, and sometimes it looks a little bit bigger. And even with these changes, Aristarchus' second clue was absolutely right. The moon and the sun have almost exactly the same apparent size. Take a piece of paper and draw any triangle you like. Now, okay, I know you won't actually take a piece of paper. So just imagine that you have a piece of paper in front of you right now and that you drew any triangle you like. A right triangle, a tiny one, a huge one, a very skinny one. The list goes on. Let's call its corners A, B, and C, and its angles A, B, and C. Now, grab a protractor, measure the three angles, and add them together. You'll always get 180 degrees. Yes, that's a rule that works for every single triangle. No matter what it looks like, the three angles will always add up to 180 degrees. But why? It's actually very simple. Draw a line through point C, parallel to a segment AB. Then, extend the segments AC and BC beyond point C. Now, look carefully. Around point C, each of the triangle's three angles appears twice. Together, they fill up an entire circle. And a full circle measures 360 degrees. So, the three angles of the triangle must add up exactly half of that, 180 degrees. This rule is incredibly useful. If you know any two angles of a triangle, you can always find the third one. Even better, if you know the triangle is the right triangle, you only have to calculate one angle to know all of the angles. Let's look at a real-world example. Imagine putting a ladder against a wall. You want to know the angle between the ladder and the wall at the top. Do you really need to put on a helmet and climb all the way up there like a circus acrobat just to measure the angle? Of course not. The wall makes a perfect right angle with the ground. So, just measure the angle between the ladder and the ground. That tells you the angle at the top of the ladder without taking even the slightest risk. And this is exactly why ancient astronomers loved looking for right triangles. Not because they didn't want to take a risk, but because right triangles made their calculations much easier without having to travel to impossible places. Pretty clever, right? One famous example happens when an object, like Venus or the moon, appears exactly half illuminated by the sun. At that moment, the angle between the Earth and the object and the sun is the right angle. Aristarchus used exactly this trick to find his third clue. And that's where things get really interesting. During a full moon, the moon is completely illuminated and the sun, the Earth, and the moon are lined up. During a new moon, the moon is completely in the opposite direction from the sun. But what happens in between? What happens when exactly half of the moon is illuminated and the other half is in darkness? Let's draw it. First, We draw the moon exactly half illuminated. Because the moon appears exactly half illuminated from the Earth, we know that the Earth must be somewhere along the axis of the moon's shadow. Let's place the Earth somewhere on that line. Now, the moon is illuminated by the sun. So, the sun must be somewhere exactly in front of the illuminated half of the moon. That means the sun is perpendicular to the axis of the moon's shadow. Do you see where I'm going? That's right! The Earth, the moon, and the sun form a right triangle, the astronomer's best friend. Now, let's place the sun somewhere along this line. For example, here I've placed it twice as far from the Earth as the moon is. Because this is a right triangle, and the angles of a triangle always add up to 180 degrees, the angle at the Earth and the angle at the sun are closely connected. If one gets bigger, the other gets smaller, and their values depend only on how far away the sun is. Let's look at some examples. If the sun is twice as far away as the moon, the angle at the Earth is 60 degrees, just like in our drawing. If the sun is 100 times farther away than the moon, then the angle is about 89.5 degrees. Okay, drawings are great, but what happens in real life? If you wait until the moon is exactly half illuminated and measure the angle between the moon and the sun, what do you think we'll find? 60 degrees, 70 degrees, 80 degrees, or even maybe 67 degrees? Aristarchus asked himself exactly the same question more than 2,000 years ago. At first, he didn't calculate the exact angle, but he noticed something very important. The angle seemed to be very close to 90 degrees. That meant the sun had to be very, very, very far away. Since the sun and the moon appear almost the same size in the sky, that meant the sun had to be enormous. Look at these images. With the same distance between the Earth and the sun, as the sun gets bigger, the shadow gets smaller. If the sun is very, very big, it will have almost the same apparent diameter whether we look at it from the Earth, from the moon, or from the tip of the Earth's shadow's cone. This was Aristarchus' third clue. Now, he had everything he needed to calculate the size of the moon. Aristarchus had found his 3 clues, and now he could finally use them to calculate the moon's size. You are going to see how simple the idea is with just one drawing. First, we place the sun over here on the left, then the Earth and its shadow cone. The shadow is a cone because the sun is much bigger than the Earth. Let's call the cone's angle angle A. This angle corresponds to the apparent diameter of the sun as seen from the tip of the shadow cone. And because the sun is extremely far away, it is almost the same as the sun's apparent diameter as seen from the Earth. Remember this, because we'll need it very soon. As the Earth's shadow travels towards the moon, it gets narrower. But by how much? By only drawing one simple line, we can easily see that the shadow narrows at angle A, which is the sun's apparent diameter, and also the moon's apparent diameter, as seen from the Earth, of course. So, at the moon's distance, the Earth's shadow has become narrower by the size of an object that, when seen from the Earth, has the same apparent diameter as the moon. What is that object? The moon, of course. So, at the moon's orbit, the Earth's shadow has lost 1 moon's width. And Aristarchus measured the remaining shadow to be about 2 moons wide. So, 2 plus 1 equals 3. The Earth is 3 times wider than the moon. And that's it. Aristarchus had found a ratio of about 3 to 1. And using our own measurements, we get about 3.73 times. And the real value is 3.67 times. Not bad at all. Just imagine, this was 2,000 years ago. No telescopes, no calculators, just observations, logic, and drawings. Impressive, right? And by the way, I slightly simplified Aristarchus' original demonstration to make it easier to understand. If you want to see his actual geometry and calculations, scan this QR code or go to this link. And by the way, all of this information is from this QR code or from this link. But Aristarchus wasn't finished yet. He wanted to calculate the distance to the moon. And we'll see how in the next video. So see you guys in the next video. Bye.